Electrons were discovered by J. Thomson through the cathode ray tube experiment. He also studied different properties of the cathode rays, which were later called as electrons, and at the same time, he was able to calculate its charge to mass ratio. Millikan, another scientist, calculated the charge on electrons. In this session, we'll discuss these two experiments, how J. Thomson calculated the charge to mass ratio of electrons and how Millikan was able to calculate the charge on electrons. So stay tuned. So the charge to mass ratio of electron was determined by J. Thomson through the same cathode ray tube experiment through which he actually discovered electrons. This experiment was done in 1897. Let's see how he calculated the charge to mass ratio of electrons. So we have a slightly modified version of the cathode ray tube that he had used in the discovery of electrons. But again, it has the same components. As you can see, it has a glass tube and there are two electrodes, that is the cathode and the anode, connected to the negative and the positive terminals of the battery respectively. And we have this fluorescent screen here, or the fluorescent material present here. So when you turn on the voltage and evacuate this glass tube, rays are emitted from cathode, which we call the cathode rays, and because of this slit that is present in the anode, they pass through the anode and strike this fluorescent screen. So what J. Thomson did was that initially he used a simple cathode ray tube in which there was nothing extra used, and so these rays went through this hole in the anode, and following this straight path they struck this fluorescent screen at point B. Later on, he decided to see the effect of electric and magnetic fields on the cathode rays or the electrons, because you know that the cathode rays are charged particles which are moving in a straight line from cathode towards the anode. So these moving charges can be affected by magnetic field as well as the electric fields. So when he applied an electric field, you can see these two terminals. The positive terminal is on top here, the negative terminal is at the bottom. And because these cathode rays are negatively charged, they will be bent or deflected towards the positive terminal. So under the influence of an electric field, these cathode rays, following a straight path, when they pass through this electric field, they strike this fluorescent screen at point A because they are deflected towards the positive end of, or the positive terminal of this electric field. Then he turned off the electric field and switched on the magnetic field. And when he turned on the magnetic field and again produced these cathode rays, he saw that they were deflected by the magnetic field, and now they strike at point C on the fluorescent screen. And then he kept both the electric field and the magnetic field on and adjusted their strength or their power in such a way so that these cathode rays strike point B again. Or in other words, he made them follow the straight path again and strike the fluorescent screen at point B. So from this, he was able to calculate the charge to mass ratio of electrons by adjustment of the electric and magnetic fields, and he came up with the conclusion that the charge to mass ratio of electrons is 1.7588 into 10 to the power 11 coulomb per kilogram. Millikan was able to determine the charge or measure the charge on electrons through his oil drop experiment. The experiment was actually performed by his student. So the experiment was done in this chamber. It's a cross section of the Millikan oil drop chamber, and you can see in this chamber that it has two plates, uh, plate A and plate A prime. These are the two electrodes. Plate A, which is on top, is connected to the positive terminal of the battery, and this plate at the bottom is connected to the negative terminal of the battery. And so this is the cathode, and plate A is the anode. You can see a small hole, a pinhole here in plate A, that is the anode. Here is the atomizer. Now, what this atomizer does is that it is filled with oil and it sprays oil in the form of small droplets above this plate A or the anode. So, this chamber is filled with fine oil droplets. This is empty here, and here we have a microscope or a telescope, because these droplets are very fine, and to observe them individually you need a telescope or a microscope. So anyone observing these droplets or performing the experiment can weave through this telescope to observe these oil droplets individually. Now, what Millikan did was he sprayed oil through with the help of this atomizer above anode, and some of these oil droplets penetrated this pinhole and they went downwards towards plate A prime, that is the cathode, under the influence of the gravity. So they had a particular kinetic energy or velocity downwards because of the gravity. So V1, that is the velocity of the oil droplets going down, is directly proportional to the gravity. So, or in other words, it is dependent upon the gravity, or the oil droplets go down with the help of gravity, under the influence of the gravity. Here you can see another slit through which X-rays were made to fall and strike on these droplets. So what they do is that these oil droplets get charged, they attract electrons, or they get electrons from the X-rays, and so they get charged, and they are now negatively charged. So to start with, these electrodes were not connected with the battery, and these oil droplets, upon penetration through the pinhole, they went down with gravity, and then X-rays were made to fall on these droplets, converting them into negatively charged droplets. And at the same time, voltage was applied through these plates. And you can see that because plate A is positively charged, or the anode is on top here and the cathode is at the bottom, and these droplets get negatively charged because of the X-rays, these will be repelled by the cathode, which is down here, and attracted by the anode. What Millikan observed was that some of these droplets, they slowed down, some of them even moved up towards the anode rather than going down with the gravity, while some of them, they were even suspended midway between the two plates. So now we have another velocity, and this velocity is actually dependent upon the voltage that is applied between the two plates and the charge on the electron, or the charge on the droplets. And this is minus mg, that is gravity. So gravity is pulling the droplets down, but the electric field is pulling these droplets up. Now, if the gravity is more stronger than the electric field that is applied between the plates, these droplets will still go down, but with a slower velocity. If the electric field is much stronger as compared to the gravity, these droplets will defy gravity and start moving up. So if we can adjust the voltage between the two plates in such a way that these droplets are now floating midway in the air between the two plates, now they will be stuck here and they will neither move up neither move down, because now the electric field is exactly equal to the gravitational force that is pulling the droplets down. Now, these droplets can be of different masses. Through this telescope, individual droplets were observed. And later on, with the help of the masses of the droplets and the charge that each droplet has, because some of these droplets may be multiply charged. Some of them might have -1 charge, others might have -2 charge, -3, -4, and so on. So each of these droplets will be suspended midway in the air with the help of a different electric field. Some of them will require a higher field, others will require a lower field. But interestingly, what Millikan observed was that for each different droplet, the electron, the electric field that was required was a multiple of 1.6022 into 10 to the power minus 19 coulombs, from which he concluded that one electron has a charge equal to 1.6022 into 10 to the power minus 19 coulomb. A droplet having more than one charge would require a stronger electric field, and that is again a multiple of this value that Millikan got at the end. So this is how Millikan was able to determine or measure the charge on electron. So now we have the charge to mass ratio of the electron. We have the charge on electron, and from this we can actually calculate the mass of the electron. So we know the charge, that is 1.6 into 10 to the power minus 19 coulomb. We know the charge to mass ratio, that is 1.75 into 10 to the power 11 coulomb per kg, which means that because we know the E, so 1.6 into 10 to the power minus 19 divided by m is equal to 1.75 into 10 to the power 11. Calculating for m, this is equal to 9.1 into 10 to the power minus 31 kg, which is the mass of a single electron. So it is actually difficult to extract one electron out of the atom and calculate or measure its mass or charge, but this is because of some ingenious experiments from Millikan and of course from J.J. Thomson, that they were able to determine the charge and the charge to mass ratio, and from which we actually calculated the mass of electron as well. So this is it about the electron. In the next session, we'll talk about the discovery and the properties of protons. So see you next time with a new topic. Thank you so much for now.